Okay, hi everyone. So in this tutorial video, we're going to be discussing on solving a few questions related to complete metric spaces, sequences, and Cauchy sequences. So in this first question, we have XD is a metric space, and Xn and Yn are two Cauchy sequences in X. We want to show that the sequence given by the distance between xn and yn, so we're making a sequence of those terms, converges in R with respect to the usual metric, which is the modulus in R. Okay, so first let's just recall what is a Cauchy sequence. Okay, so we say that a sequence, and of course this is for any general metric space. So a sequence xn in a metric space, let's say x comma d, is a Cauchy sequence if for any epsilon or given any epsilon positive, there exists or there is a natural number, call it capital N or big N, such that for if you take any two other natural numbers, m and n, so m and n are two natural numbers, and these two natural numbers are bigger than big N or greater than or equal to, it doesn't matter. We have that the distance between xn and xm is less than epsilon. Okay, so that is the definition of a Cauchy sequence. So in this question, we are given two such sequences, xn and yn. So let's just sort of maybe try to visualize what's going on here. So this first sequence, x1, x2, x3, x4, and we keep going, xn, right? And we keep going. And then we have another sequence, call it yn, given by y1, y2, y3, y4, yn, and we keep going. This guy here is a Cauchy sequence. This one here is also a Cauchy sequence. So the sequence that they are referring to, this one, d of x and yn, what exactly is that sequence? So what we're going to do is we're going to measure the distance between corresponding terms in the x and the y. So what do I mean? I mean that we're going to measure the distance between x1 and y1. Okay, and that of course you know is is given by d of x1, y1, right? So we're measuring the distance between those two terms, and then I want to measure the distance between x2 and y2. Okay, so the distance between x2 and y2, and so on, right? So we continue in this way, measure the distance between x3 and y3, x1, y4, xn and yn. Okay, so we continue in this way. We have the distance between xn and y, and we continue doing this. Now remember that the output from a metric, d, is a real number. So this forms a new sequence. So we could call this new sequence maybe c sub n. This forms a new sequence, and where each of these terms are real numbers. So the original sequence xn and yn, we don't know what those terms are because we don't know, or we may not have specified what the metric space X is. Okay, so X and Y could be functions, for example. But the sequence Zn, this is a sequence of real numbers. Okay, so this is a sequence of real numbers. So we converted or we form a link between the two sequences that we started with, xn and yn, which may not be numbers, to form this new sequence, which is a sequence of real numbers. What we are asked to show is that this sequence, Zn, converges in R. And I guess you probably may guess that what we're going to exploit here is the fact that the real numbers is a complete metric space. So essentially what I want to do is show that this sequence Zn, if I could show that this sequence Zn, a sequence of real numbers, is a Cauchy sequence, it's in the real numbers. Therefore, it will converge. So maybe let me write here d of x and yn, right? So if you want to, you can call it Zn. It doesn't matter. Okay, so you can define it to be, I guess that should be the opposite way. Zn should be defined to be d of x and y. Okay, let's just leave it like that. All right, so the proof goes like this. Let's see how we can prove this. So proof, so required to prove that the sequence Zn converges. And notice that this sequence is a sequence in R, right, with the usual metric in R, which is a complete metric space. Okay, so therefore, it is enough to show that this sequence Zn is a Cauchy sequence in R, because we know R is complete. So it is enough to show that the sequence Zn is a Cauchy sequence. Okay, so that is actually going to be my aim. This is going to be my aim. Okay, so what does that mean? That the sequence Zn is a Cauchy sequence. So maybe we could write this as an aside, just so we know what we are aiming for. Okay, what does it mean for Zn to be Cauchy? Right, what does it mean for Zn to be Cauchy? Well, so that means that for any epsilon bigger than 0, of course, you could find there exists the m. So there exists maybe a natural number n, such that if you take n and m bigger than this guy, we have that the distance between Zn and Zm is less than epsilon. So this distance between Zn and Zm, okay, maybe I shouldn't have put D there because because you might think that's the same metric as x. Okay, so Z is a sequence in R. So the distance in R we use, we're told it's the usual metric. So it's just a modulus of Zn minus Zm. Okay, so I just want to write this so we see what exactly we need to aim for. What is this equal to? The modulus of Zn minus Zm. So Zn, okay, so that is, by definition, Zn is the distance between xn and yn. Remember, that is the way we defined it up here. Okay, so just rewriting what the z's are. So this guy minus and zm is the distance between xm and yn. Okay, so this is actually what we are after. Okay, so So there's a couple ways we could prove this. There's actually an easy way to do it, and that is to notice that move this up a bit. And that is to notice that this is equivalent. So a sequence B in Cauchy is equivalent. In other words, okay, if I tell you a sequence, Xn is a Cauchy sequence, then this is the definition for it. But there's another way to write it. So in other words, Xn is Cauchy if the distance between 2 points goes to 0, as n and m goes to infinity. Okay, you could prove that these two are equivalent. So one way, so this is actually the easier way to do it, or so we could either do it that way, or we could show that the modulus of Zn minus Zm goes to 0 as n and m goes to infinity. Okay, I claim that this statement and this statement are equivalent. Okay, and that's just something you could sit and just think about it for a minute or two, why those two mean the same thing. Because if you can make the distance between xn and xm arbitrarily small, then that means the distance must be going to 0. Okay, so that's actually what our target is going to be. Okay, so let's start the proof. All of that was sort of like an aside to the proof. Okay, so suppose xn and yn are Cauchy sequences in X, then by definition of a Cauchy sequence, what we just discussed up there, we could say that, and you could do it the epsilon way, by the way. We could say that for any epsilon, there will be a natural number n1 for this guy and a natural number n2 for this guy, such that the distance between any two terms is less than epsilon. In that case, you could probably take it to be epsilon over 2 because you might end up adding something in the end. But there's an easier way to write it, and that is by definition, the distance between the terms in the x's is going to 0, and the distance between the y's are going to 0 as the natural numbers n and m go to infinity. Okay. So my aim is to show that this thing here is going to 0. Okay, so what I want to do is maybe consider, okay, so I want to try to build that inequality you see up there. So what I could do is consider the distance between xn and yn, right? And notice that it's the modulus of this, and there's a xm and ym. Okay, so I need to bring that in. So how do I bring in xm and ym into this? So I could use triangle inequality, and I could jump from xn to xm, right? And then I could jump from xm to ym, right? That's the term. So I'm trying to get this term into the story. Okay. And now to finish off this triangle inequality, I need to jump back from ym to yn. Okay, and that means that d of xn, yn minus, so I'm going to take this guy over, d of xm ym is less than or equal to d of xn xm plus d of ym yn. Okay, and we could call this guy 1 maybe. And by a similar way, we can construct another inequality. Right, so that similar way we could so you can think of it like if you interchange n and m, or let's write it out similarly. I could write something like this. I could maybe write d of xm ym, and now I need to bring in n xn yn into the story. So I could go from d of xm to xn, plus then I could go from xn to yn, right? So now I have this too, which is what I want to bring into the story. And to finish it off, I need to go from yn back to ym. Okay, so that again is just triangle inequality we're using to make these inequalities. And I'm going to bring the d of x and yn over to the left. So I get d of xm ym minus d of xn yn is less than or equal to d of xm xn plus d of yn ym. And I could call this guy 2. So from 1 and 2, we could combine both of these. Okay, so from 1 and 2, we could combine both of these. So from 1 and 2, if you combine both of these inequalities, then notice that what I have on the right-hand side of 1 and 2 are the same. Okay, but if I take 2 and multiply through by a minus sign, I will get minus into d of so take 2 and multiply through by a minus sign, so I'll get minus into d of xn, and I'm just switching the m and the n around, plus d of yn ym, okay, and that will be less than or equal. So from 2, if we multiply through by a minus sign, this will be d of xn yn minus d of xm ym, and then from 1, if we apply 1 to this guy, you see that this guy is less than or equal to d of xn xm plus d of yn ym. Okay, but this is the same thing as saying that the modulus of d of xn yn minus d of xm ym is less than or equal to d of xn xm plus d of yn ym. Okay, and this goes to 0 as n and m goes to infinity. Because remember, this guy goes to 0, this guy goes to 0, because they are both Cauchy sequences, right? They are both Cauchy sequences. Up here is where we have that. Okay, so therefore, and these terms that you see here, this is just your Zn, and this is your Zm. So what do we have? Therefore, the modulus of Zn minus Zm goes to 0 as n and m goes to infinity. In other words, the sequence Zn is a Cauchy sequence. okay, which is what we wanted. Right? Remember, we said that that was our aim. If we could show that Zn is a Cauchy sequence, well, these are just real numbers, so they will converge. Uh, so the sequence Zn converges since R is complete. Okay, so that's this first proof. Okay, so in this next question, we are given the space of all continuous functions on closed interval -1, 1 with the following metric. So the distance between any two such functions, we're going to define it to be a square root of the integral from -1 to 1 of the modulus of the difference of these functions squared. Okay, so this is sometimes called the D2 metric. And essentially what this question is going to try to prove or try to show is that this space, the space of all continuous functions on this particular interval, equipped with this metric is not a complete metric space. So it's not complete. So if I want to show it's not complete, I need to find a sequence. In this case, it's a sequence of functions that is a Cauchy sequence, and show that the limit, or if it converges, that that limit is not in this space. So it's converging to something outside of the space, which means as part of this metric space is concerned, it's not converging. So we need to find a Cauchy sequence that does not converge in this space. Well, we're given what one possible sequence is to do that. Okay, so there are many counterexamples you could come up with. This is just one of them. So consider the sequence of functions, and so maybe X wasn't the best choice here because they use X as the argument, but we'll just have to keep that in mind. That's not a big problem. So consider this sequence of functions, xn in this space, defined by, so it's defined piecewise. So between -1 and 0, it's defined to be 0. From 0 to 1 over n, it's defined to be nt. And from 1 over n to 1, it's defined to be 1. Our first task is we want to show that this particular sequence is a Cauchy sequence. And then the second part is they're asking us to determine if this metric space is complete. So for this particular example, it really helps. It's not necessary to do this question, but it really helps if we have an idea or a drawing of what these functions look like. Okay, so it's defined on the interval -1 to 1. Maybe this height here is 1. Okay, and so let me just draw two such functions. So two such functions, I'm going to take, for example, m bigger than n. Okay, and m and n are natural numbers. So if m is bigger than n, then, so I'm just taking two natural numbers, then 1 over m is less than 1 over n. Okay, we'll see why that will be, that will come in handy in a bit. So the first function, which I'll draw in red, so I'm just following the definition given here. It's 0 from -1 to 0, okay. And then from 0 to 1 over n. So 1 over n will be less than 1. So let me maybe put 1 over n over here. Okay, so I'm going to do that in the next color. Right, so this guy here is 1 over n, and 1 over m, we know it's less than it. So that's 1 over m, and this guy is 1 over n. Okay, so from 0 to 1 over n, it's nt. Okay, so that's the equation of a line. In fact, that's the equation of a line having gradient n, right? And if you work out what 2 points of this line works out to be, 1 point on this line is 0, 0, and another point on this line, you could just work it out, is 1 over n, 1. So to draw a line, we just connect those 2 points. So 1 over n, 1 is this guy up here. So I'm just going to connect these 2 points. Right? So that should be a straight line. And from 1 over n to 1, it's just constant, 1. Okay, so this guy here is xn. Okay, that's one of the function in this sequence. So that's one function. And I'm going to draw another function for m. So I'm going to draw xn, sorry, xm. So I have xn, I'm going to draw xm. Xm is the same between -1 and 0. It will also be 0. Okay. And a point on xm, is the origin, and 1 over m, 1. Okay, so you see that as the natural numbers increase, the slope is getting steeper, right? And then it's constant at 1. Right? So the slope is getting steeper. So this guy here is xm for m bigger than n. Okay, so we could take with our loss of generality m bigger than n. Okay, so these are just two arbitrary terms in this sequence of functions. So our task is we want to show that this sequence is a Cauchy sequence. So required to prove or required to show that this sequence of function xn is Cauchy. Okay, what does that mean? That basically means, so we saw from the last example that the distance between any two terms, xm and xn, the distance between these terms are going to 0 as n and m go to infinity. Okay, and this distance, we are given it in terms of the D2 metric. So this is our task. So we just need to essentially integrate this, the difference between these two functions from -1 to 1, and then take the limit as n and m go to infinity and see what happens. Does it go to 0? So let's try to do that. Okay, so let's see how to do that. So let's say without loss of generality, right? I could take two natural numbers, m and n are two natural numbers such that I'm just going to take m. Let's just say m is the bigger one, right? M is the bigger one. So I'm looking at these two functions that we just drew up here. So I'm going to consider. So what do I want? I want the distance between two of them. I'm going to give myself a little space because it's going to be a bit right. So I'm going to consider the distance between xm and xn. But if you look at the equation for the distance, it's given by the square root. Okay, it's a square root of the integral. So to save myself that hassle, I'm going to take this guy squared. Right, and let's just consider it, because actually if you think about it, this is the same. This is the same as saying the distance squared goes to 0 as well. Okay, so we could either show that the distance between any two terms is going to 0, or if you wanted to, you could equivalently show that the distance between two terms, if you square them, that's also going to 0. Okay, so this is another equivalent way. And again, what the square does is it allow us to not worry about the square roots. So we don't have to worry about writing the square root every time. Okay, so by definition of the D2 metric, this is the integral from -1 to 1 of the modulus of x m minus x m. So it should be x m of t, right? So the dummy variable we're integrating over is t. Okay, so I'm getting the difference between them. Take the modulus, square that guy, integrate with respect to the dummy variable, right? And I know in the definition of the metric, you see is f of x, g of x integral with respect to x. Okay, but remember, that's just a dummy variable, right? You could call this any variable you like. So I'm just calling it t because we labeled the functions x. Okay, so I'm calling it t. Okay, so I want to work out what this is. Um, Notice that since we're squaring the difference, the modulus there is a little bit unnecessary. It would have been necessary if these functions were, let's say, complex valued, but these functions are real valued functions. So what I'm saying is that we don't really need a modulus there, right? That modulus, you could get rid of it because I'm already squaring these terms anyway. Okay, so I could get rid of the modulus. And now this is where, if you have a diagram, it comes in handy because I'm integrating essentially the different square of these two functions. But notice from -1 to 0, the functions are the same. Okay, so obviously the difference is 0. And notice from, in this particular case, from 1 over n to 1, the functions are the same. So essentially the integral will reduce to an integral over 0 to 1 over n, right? Because it's over here where they are different. Okay, so because the integral, if the two functions are the same, then the integral of their difference is 0. So this integral, no need to integrate from -1 to 1. We could just integrate from 0 to 1 over n. Okay, and okay, let's write that and then we'll break it up even further. So this is the same as the integral from 0 to 1 over n, right? Maybe let me switch the brackets. M minus xn of t squared dt. Okay, so I changed that. And again, let's go back to our drawing. Notice that the function xm, the blue one, changes its behavior at 1 over m. Okay, so I need to break this integral up a bit further because I'm integrating piecewise defined functions. So I'm going to break up this integral as the integral from 0 to 1 over m. Okay, and then the blue function changes its behavior. Then we're going to go from 1 over m to 1 over n. I'm just going to break it up further. Okay, so all of this is just a task that you all would have done in your undergrad calculus where you have to integrate these sort of functions. So this is the same as if I go from 0 to 1 over m, I think it was, okay, of something. So we'll fill in that in a bit, plus the integral from 1 over m, 1 over n of something. Okay, so from 0 to 1 over m, what does xm look like? From 0 to 1 over m, xm looks like mt, not mt, m times t. Here's m times t, and here's n times t. Okay, so it looks like m times t. And the other guy, the red one, is n times t. So from 0 to 1 over m, from 0 to 1 over m, the blue function is empty and the red function is empty. Okay. So I'm just filling in what these functions are now. So the blue function is, so it's mt minus nt. Then I'm squaring these two functions. So I'm saying this guy is this guy, and this one is this one. Okay, and from 1 over m to 1 over n, what do these functions look like? So from 1 over m to 1 over n, the blue one is 1, the blue guy is 1, and the other guy, the red guy, is nt still. So this one is 1 minus, and the other guy is nt still. Right? Square dt dt. Okay, so now we just need to work out these things out. So let's expand it out and then we'll integrate it. So 0 to 1 over m. So let's expand this. So this is m squared t squared plus n squared t squared minus 2mn t squared. Okay, plus integral 1 over m to 1 over n. Let's expand this out. So this is dt. Okay, if I forget the dt, of course, you know it's the integral over t. dt. So this guy is 1 plus n squared t squared minus 2nt, not squared, just squared it, dt. Okay, great. So now we can integrate. Let's see. So m squared t cubed over 3 plus n squared t cubed over 3 minus 2mn t cubed over 3 evaluated from 0 to 1 over m plus, and the next guy is and the next one is t plus n squared t cubed over 3 minus, okay, that's right, minus 2n t squared over 2, star and that one will cancel, from 1 over m to 1 over n. Okay, so now let's stop in what all these things are. So when t is equal to 1 over m, I get 1 over m. So I'll simplify it down a bit. Notice in this first bracket, we have in common t cubed and 1 over 3. So I can actually simplify this one a lot. Yeah, let's do that. So what I'm saying is that I could write this first bracket just to make my life easier. That's m squared plus n squared minus 2mn t cubed evaluated from 0 to 1 over m. Right? Plus this one will be t plus n squared t cubed over 3 minus the 2's cancel nt squared. All right, so I'm hoping I don't make a mistake because then it may not go to 0. Remember, what I want to do is whatever expression I end up with in the end, I'm going to let m and n go to infinity, and hopefully that expression is going to go to 0. And that will tell me that this sequence is a Cauchy sequence. Okay, so this first is just 1 over m cubed. Okay, so this whole thing is 1 over m cubed. Yeah, so we got m squared plus n squared minus 2mn all over 3m cubed. Right, that's what this first guy will be. Plus 1 over n. So let's see. I have 1 over n plus, so I got 1 over n cubed by n squared is 1 over n, so this is 1 over 3n minus, and I got 1 over n squared by n is 1 over n. Okay, now I'm going to minus from that 1 over m. So this is 1 over m plus n squared 3m cubed minus n over m squared. Yeah. Okay. All right. So let's see. Let's see if anything here simplifies. So this guy, what remains the same? M squared plus n squared minus 2. Actually, I think this is m minus n all squared. Yeah. Anyway, let's see. We'll see later. Plus, so this guy, the 1 over n minus 1 over n cancels, and I get 1 over 3n minus 1 over m minus n squared over 3m cubed plus n over m squared. Okay, so now I need to combine all this into one fraction. So the LCM is m cubed n. Yeah, m cubed n. So m cubed n, right? So we could do 3 here one time. 3m cubed n. So this is just m cubed and minus 3m squared n. Yeah, and 3m cubed minus n cubed. Okay, and then this guy is m squared, so that's 3mn by n, 3mn squared. Okay. Right, so let's combine everything now. 3, and hopefully I didn't make a mistake. 3mn LCM. So this will still multiply everything by n. So m squared n plus n cubed minus 2m m n squared. Anything simplifies here? No. Plus m cubed minus 3m squared n minus n cubed plus 3m n squared. Okay, n cubed I'm seeing cancels. Okay, let's see what cancels. This guy cancels with this guy. M squared n squared n. I have a minus 2m squared n. So let's write that. So 3m cubed n. So m squared n minus 3m squared n is minus 2m squared n, okay? And mn squared, mn squared. So minus 2mn squared plus 3mn squared is plus mn squared. I have a m cubed plus m cubed, okay? All right, so let's see what this simplifies. Maybe I put this guy here. Right. This is equal to so they all have m in common, right? Everything has an m in common, so I could strike a m out. So the denominator now becomes 3m squared n, right? And the numerator becomes, so if I strike out an m, I get a m cubed goes down to m squared, minus 2mn plus n squared. And I believe the numerator could factorize as m minus n all squared, all over 3m squared n. So hopefully I didn't make any mistake, right? And now what you want to do is you want to send m and n to infinity. So this will go to 0, but I'm trying to see where we could do it. So maybe, yeah. So here's what we're going to do. We're going to divide every term by m squared n squared. We're going to divide every term by, we're going to multiply everything by this, right? So divide every term by that. So if I divide m squared by m squared n squared, I get 1 over n squared. If I divide this guy, I get minus 2 over mn. If I divide n squared by m squared n squared, I get 1 over m squared all over. And if I divide this guy, I get 3 over n. Okay, so divide everything by m squared n squared. Now it's easier to see what will happen, right? So now it's easier to see. M squared n squared. Actually, um, no, then the denominator is going to 0. Um, I think, yeah, maybe I should have just divided by m squared alone. M squared, yeah, so that would have been bottom. So divide by m squared alone, not m squared n squared, m squared alone. Or maybe m squared n. So what I'm saying is we could write this as 3m squared n minus 2mn over 3m squared n. Yeah. So maybe this way is better. Okay, so I'm just writing out each individual term. And this first term is 1 over 3n. The second term is 2 over 3m. This third term is n over 3m squared. Yeah, it's easier to see here. So all of these are going to 0 as n and m goes to infinity, right? So that's clear from the first term is going to 0, the second term is going to 0. The only term that you might be wondering a bit about is this last term. If you have n over m squared, why is this going to 0 as n and m go to infinity? Because you might be saying, well, isn't the numerator going to infinity? Yeah, the numerator is going to infinity, but the denominator is going to infinity faster. Okay, if for example, if I what is bigger, x or x squared? If I say x goes to infinity, right? X squared is going to infinity faster than x. Okay, so essentially what I'm saying that is that the denominator is going to win, right? And you can make that idea even more rigorous if you apply one of those rules in calculus, but we don't need to at this point. Okay, so that guy is going to 0. Therefore, what did we just show? We showed that the distance between xn and xm squared is going to 0, which is the same or equivalent to the distance between xn and xm going to 0 as n and m go to infinity, which means that this sequence of function is a Cauchy sequence. So this sequence of function, xn, is a Cauchy sequence. Okay, so that's the first part. So the first part was a bit long because we had to do this sort of calculation. But the idea is to go through it kind of slow and try not to make any mistake because it's easy to make like a mistake with a minus sign and then things don't cancel. Things don't cancel in the end, and you wonder why it's not going to 0. Because remember, if when you take that limit, this limit in the end, if it's going to anything except 0, if it's like going to 1 or a half, then it's not a Cauchy sequence. It needs to go to 0. Right? That 0 is crucial. Okay, so the second part in the proof is asking us, hence determine if this metric space is complete. So what we just proved is that this sequence of function is a Cauchy sequence. And now they're asking us about it being complete. So the next question is, if this is a Cauchy sequence, could we try to guess or figure out maybe what this sequence xn might be converging to? And again, the diagram will help us. And well, you actually don't need a diagram. You could figure it out from the piecewise definition of the function. As n goes to infinity, what function is this approaching? So as n goes to infinity, it's easy to see that this middle term just goes away. And it just becomes 0 on the left of 0 and 1 on the right of 0. And there's a jump at 0. Okay, so let's try to make that a bit more rigorous. Okay, so for part 2, right, I'm going to define this function, x of t. Okay, and it's going to be 0 on the left of 0. So 0 if t is less than or equal to 0. Plus or minus 1. Let me just make sure the inequality sign is the same. Actually, yeah, it doesn't matter where we define it to be. I think these signs, yeah, so it's equal to 0 at 0. Yeah, it's equal to 0 at 0. So this essentially what I was just checking there was the sign. I wanted to know if this sign should be less than or equal or strictly less than. But from the definition of xn of t, the terms in my sequence, it's 0 if minus 1 less than t less than equal to 0. So at t equals 0, xn of 0 is always 0. Okay, because we include 0 here. So xn of 0 is always 0. Therefore, this is going to, if we do have a limit function, which I'm trying to come up with, this limit function that I'm calling x at 0, that will be 0 as well, Okay, so that's why I include the equal part here. Okay, ideally that doesn't really matter because it's going to have a jump there anyway, but we just want to know what, okay, if it's jumping at 0, what is the value at 0? And I'm going to define it to be 1 if 0 is strictly less than t less than equal to plus 1. Okay, so I'm going to define this function. So clearly this function is x is not in the space of continuous function from -1 to 1, right? Because it has a jump at 0. Since x has a jump, discontinuity. Okay, so it's not there. But my claim is that this Cauchy sequence is convergent to this function. Right? So my claim is that this sequence xn is convergent to x as n goes to infinity. Right? So again, how to do that? So that is equivalent to saying that the distance between the terms in the sequence, the functions, and this new function x goes to 0 as n goes to infinity. Okay, and of course we know we don't want to deal with the square roots. So instead of considering the distance, I'm just going to consider the distance squared. So I don't have to deal with the square root. Okay, so this last term, I should say this last point, this is my e. Okay, that is what I'm aiming to show. If I could show that, then that will mean that my sequence of function xn, which we just spent a lot of time proving is a Cauchy sequence, that Cauchy sequence is converging, but it's not converging to something in the space. Therefore, we cannot say it's converging. So we found a Cauchy sequence that does not converge. Okay, so therefore the space is not complete with respect to this metric. Okay, so that is my aim. Again, it's a it's a bit of a calculation we have to do because it's an integral. Okay, so I'm going to consider what is the distance between xn and this guy x squared. Okay, so we know that is integral from -1 to 1 of xn of t minus x of t squared dt. Again, we know that the modulus there is a little bit repetitive, and I could get rid of the modulus because these are just real valued functions, and I'm squaring it anyway. And again, if I look at this limit function, it's 0 from -1 to 0, so it's the same as xn. What is xn? xn xn is 0 from -1 to 0. So that integral, no need to integrate from -1 to 0, right? I can instead just integrate, and it's 1. So draw the limit function then. The limit function is this guy. So it's 0 from -1 to 0. It's 0 at 0, and then it jumps. Right? So this is the limit function then. Yeah, so that's the limit function. So we see from 1 over n to 1. From 1 over n to 1, the limit function and xn are the same. In other words, this integral is just going to boil down to the integral between 0 and 1 over n, just like before. Right? So what I'm saying is that no need to integrate from -1 to 1. We could integrate instead from just 0 to 1 over n, because that is where these two functions differ. Again, no need to take the modulus because I'm squaring it anyway. Okay, and now we could just write down what these functions are. So from 0 to 1 over n, xn, we know looks like nt. And from 0 to 1 over n, well, the limit function is either 0 or 1. So from 0 to 1 over n, the limit function x is just 1 squared dt. Right, and again, we have to, I think, do we integrate this? No, we didn't integrate this. Okay, so the integral of this, expand it out to x n squared t squared plus 1 minus 2 n t, integrating from 0 to 1 over n dt, right? Yeah, and this will become n squared t cubed over 3 plus t minus nt squared, because the half will cancel with 2, evaluated from 0 to 1 over n. So when t is equal to 1 over n, this becomes 1 over 3n, right? Yeah. N cubed, yeah, 1 over 3n plus 1 over n, yeah, minus 1 over n. And when t is equal to 0, everything is 0. Okay, so that's just 1 over 3n, which of course goes to 0 as n goes to infinity. Okay, so therefore, we have showed that the distance between the terms in my sequence, these functions xn and this limit function x squared, goes to 0 as n goes to infinity, right? And we of course know that also means that the distance, instead of the distance being squared, just the distance goes to 0 as n goes to infinity, and this is equivalent to saying that the sequence xn converges to x. Well, I shouldn't say it converges because it's convergent where, right? So maybe I can't write that, right? So now we say, however, x is not in the space, so xn cannot converge, or maybe does not converge in the space. That is, the space is not complete. Right. Also, an interesting thing to note, I think it's in the course notes, is that an interesting point, this same space, see, maybe not from -1 to 1, but on any closed unbounded interval AB. So the continuous functions on any closed bounded interval AB with the supremum metric. Right? So remember what this is? This is just the supremum of the difference between the functions, where t in this case lies between a and b. Of course, since these functions are continuous and a closed bounded interval ab is compact, this supremum we could say is the maximum, but it will give the same value. So supremum, maximum, same thing. Is complete. So this space with this metric is complete, is a complete metric space. Right? So if we change the metric, but keep the space the same, what we saw here is that there's no guarantee the completeness will remain. Okay, so for the final question, it involves Cantor's intersection theorem, or the converse of it. So let's recall what this theorem says. It says that a metric space is complete if and only if we have for any decreasing sequence Fn, And these sets are non-empty closed sets of X such that the diameter, so the diameter of them goes to zero as n goes to infinity. Then the intersection contains exactly one point of X. So if a metric space is complete and you take any decreasing sequence of non-empty closed sets that have a diameter going to zero, the intersection of all of those sets will contain exactly one point. What we are asked to do is to prove the converse of this theorem. Okay, so proof, we're going to say that suppose for any decreasing, so I'll use this for decreasing sequence of non-empty closed sets Fn with 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 the diameter of them going to zero, we have the intersection of all of these functions is equal to only one point. So I can keep this like 1 point x. Well, maybe let's not give it a name yet. We have this intersection contains only 1 point, right? Required to prove or required to show that X is complete. Okay, so this is my aim. That is what I want to show. And the usual way to show a metric space is complete is we just need to take an arbitrary Cauchy sequence in X and try to find what it could possibly be convergent to, and then show that it does converge to that point, and that point is in the space. So we're going to consider a Cauchy sequence in X. Consider Xn consider a Cauchy sequence. Xn in X. Okay. So what does that mean? It means for any epsilon, I can find a natural number such that the distance between 2 points is less than that epsilon, as long as I take those points after this big natural number. Okay. So I'm going to let epsilon, so I want to do this for a bunch of different epsilon. So let epsilon be 1 over 2 to the I. Okay, for I equal 1, 2, 3, and so on. Okay, so it means that for each of these epsilon, for each of these 1 over 2I, then there will exist, then there exists some natural number, call it Ni, right? Call it Ni, such that if I take two other natural numbers bigger than this Ni, right, the distance between xn and xm is less than this epsilon. And of course, I take epsilon to be 1 over 2r, right? We can say less than or equal to, it doesn't matter. So in particular, what I'm going to do is I'm going to set m to be equal to this guy. because this inequality holds for any n and m bigger than or equal to ni. So let's fix one of those guys, right? So let's fix m. So in particular, in particular, in particular, for n, right, bigger than or equal to ni, the distance between x and remember I'm fixing m, I'm fixing the index m as ni, and x and I is less than 1 over 2 to the I. Right? And of course, this holds for I equal 1, 2, 3, and so on. Right? So I have a bunch of these ni's and a bunch of these epsilons, and I get a bunch of distances or a bunch of these points. And okay. Um, so so essentially what I want to do, right? So the idea is I want to make use of my assumption here. And if you look at it in the assumption, I need a lot of things going on. I need a sequence of closed sets that diameter is going to 0, and the sequence must be decreasing. So decreasing means, for example, F1 is contained in F2, and F2 is contained in F3, and so on. So they are all inside each other. So if this is F1, then F2 is in here, and then F3 is in here, and so on. Okay, so they must be closed, they must be decreasing, and their diameters must all be going to 0. Notice if the diameter is going to 0, then the radius is obviously going to 0. Uh, so how do I construct these sets? So what I'm going to do is I'm going to make a bunch of closed spheres, because a closed sphere is a closed set, right? A closed sphere is always a closed set in a metric space, and I'm going to make these closed spheres nested. So they will be one inside each other. I'm going to make it in such a way that the radius or the radii for these closed spheres are all going to 0, which means that the diameter of the sequence of sets is going to 0. So let's see how to do that. Right, so that's the strategy here. Um, so we could say let Fi, so for each I, I'm going to let Fi be the closed sphere of radius, closed sphere centered at x and I of radius 1 over 2 to the I minus 1. Right, you'll see why in a bit. It's 2 to the I minus 1. Okay. So this is a closed sphere. Centered at x and I with radius 1 over 2I minus 1. Okay, and although we don't need a picture, it's always good to have a picture in your mind as to what's going on. So maybe let's just draw, let's draw F1 and F2, right? So F1, um, so I have here's x and 1. So when I is equal to 1, x and 1. And when I is equal to 1, I have 1 minus 1, which is 0. So 2 to 0 is 1. So it is 1 and it's closed. So I want to draw the circle to draw this the closed boundary. Right. So this guy is F1. Okay. And so notice by construction that F2 will be inside of it. Right? Why is that true? Notice by construction, F1 contains F2 contains F3 contains Fi contains Fi plus 1. Right? And the reason for that is because if you think about it, if you take any point, let's say in this set, any y in here, then that means that what does it mean to be in this closed sphere? It means that the distance between y and x n I it is less than 1 over 2 to the I. And we want to show that the distance between y and x n I plus 1 is less than 1 over oh sorry, I'm doing it backwards. That's why it's not working out. I need to take a point in this set. Yeah, I need to take a point in this set and then show it's in the next one because the inequality, the inclusion is going the opposite way. Yeah, sorry about that. So I'm going to take a y in fi plus 1. So the distance between y and x and I plus 1 is less than 2 to the I plus 1, which is less than 1 over 2 to the I. Okay. And so the only thing that could go wrong is maybe these centers and these centers need to be also nested. So maybe I should have also said let Fi be the sphere, but I also need to take these Ni's as a decreasing sequence as well. So let me write that we can take maybe we can arrange and one because if you take xn, if the distance between xn and one is less than a half, then the distance, then if you make this smaller, instead of a half, it's a quarter, then you need to go further out in the sequence. So n1 should be smaller than n2, and n2 should be smaller than n3, and so on. Right? That's the best explanation for that. If the distance between xn and xn1 here is 1/2, right? And you want terms where instead the distance is smaller than a half, say a quarter, then you need to march further out in your sequence. So then you need to take maybe xm, where m is bigger than n, right? So that's what I'm saying here. The n's, the n1, n2, and so on, n1 must be less than n2, and n2 must be less than n3. Yeah. So then when you take a y in this set, that y will also be in this set. So how does that relate to our picture? Xn1 is in there. So we know Xn2 is also in here, right? So F1 will contain Xn1. It will also contain Xn2, Xn3, Xn4, and all of them. So that's what we need, right? Because it could, so what was happening is I wanted to ensure that Xn2 was not out here, right? So Xn2 is in here. So Xn2 is in F1. And now I'm going to take a closed sphere around this guy. So this is when I is equal to 2 of radius 1/2, right? So maybe radius 1/2. And this is F2. Okay, so these are the closed walls that I'm constructing. Yeah. So also notice by construction that the F is a decreasing sequence of closed sets, right? Because they are all closed spheres. Closed sphere is a closed set. And also the diameter of each Fn, let's say Fi, which we know is the supremum over the distances xy, where x and y come from Fi, right? And this guy is less than, so it's basically 2 times the radius. So this guy would be less than or equal to 2 times, and the radii of Fi is, so that's why we took it to be 1 over I minus 1, 1 over 2I minus 1, right? So this becomes 2 by 1 minus I plus 1, which is equal to 1 over 2, 2 minus I. Okay. And of course, this is going to 0 as I goes to infinity. Okay, so the diameter is going to 0. So by assumption, right, the intersection of all of these closed spheres has a singular point, x. Let's call him x. Right, and of course this x belongs to x. Okay, maybe not that. Okay, so my claim is that this Cauchy sequence, remember it's a Cauchy sequence we were dealing with, that's how we were choosing these points. My claim is that this Cauchy sequence is convergent to this guy, x. Okay, so claim is that this Cauchy sequence is convergent to x. If I could show that, then my space is complete. So this x is in all of the fi's, right? So since x is in fi for all I, okay, so for all I, this means that the distance between x, right? If it's, remember what the fi is, it's a closed sphere. So that means and the x is in all of these closed spheres. So the distance between xi and all of the centers for x and I, should be less than the radius. That's what it means. What does it mean to be in a closed sphere? It means that the distance between less than or equal, right? Or we could say strictly less than, it's fine. Okay, less than, less than or equal. What does it mean to be in the closed sphere? It means that the distance between that point and the center is less than or equal to the radius, 2I minus 1. Okay, so, and this holds for all I. Okay, so for all I. So if I want to show that xn is convergent to x, then if you give me any epsilon, so given any epsilon bigger than 0, we can find, or we can take an ni such that, remember how these ni's were chosen? They were chosen so n1 corresponded to a radius of a half, n2 corresponding to a radius of 1 over 2 squared, n3 1 over 2 cubed, and so on. So if you give me any epsilon, I could always find an ni such that 1 over 2 to the I is less than that epsilon. Okay, so any epsilon give me, I could always find an index I such that 1 over 2I is less than epsilon. And that tells me which of these ni I'm going to take. Yes, I could always choose the I such that 1 over 2I is less than epsilon. Then, for what happens if I take n bigger than or equal to this ni? Well, the distance between x and xn, if I use triangle inequality, the distance between x and xn is less than or equal to the distance between x and xni plus the distance between xni and xn, right? And the distance between x and xni, we know that x is in all of these closed balls, or these closed spheres. So the distance between x and xni, look, is over here, is less than or equal to 1 over 2 to the I minus 1. And the distance between xni and xn, right? Remember, xn was a Cauchy sequence. So the distance between xn and xni, well, we have that up here. That's how I was choosing or forming these closed spheres. The distance between xn and xni is always less than 1 over 2 to the I. Okay, so now we're just piecing together everything. I suppose I then need the 1 over 2 to the I minus 1. Anyway, but it still works out. Doesn't matter if it's 1 over 2 to the I minus 1 or 1 over 2 to the I. Right? And I guess in this case, I should have taken, yeah, so in this case, I'm just going to see here that I have to adjust this epsilon. So I want to put this less than epsilon. So that tells me I needed not just to take I such that 1 over 2 to the I is less than epsilon, but I needed to take I such that, not 1 over 2 to the I, 1 over 2 to the I minus 1 plus 1 over 2 to the I, right? And of course, I could always do that because as I increase it, these numbers decrease. So I needed to make it such that this guy is always less than epsilon. Okay, so this guy is less than epsilon, right? Which means xn. So what do we show? We show that given any epsilon, I could find a natural number n. This is how I do it, right? This natural number ni corresponds to this index I that I take here, such that for any natural number bigger than this ni, the distance between x and xn is less than epsilon. That means that xn converges to x as n goes to infinity, right? That's the definition for the convergence of a sequence in a metric space. Okay, so which is what I wanted to prove. So, and I know X belongs to the metric space. So X is complete. Okay, so that is the converse of Cantor's intersection theorem.